Okay, so polynomials. We're going to start off with a little review of exponent rules. So we know a polynomial just means, poly means many, mono means one, right? So a polynomial is just, it ends up meaning sum of terms. It's just going to be a mathematical function or expression that has a sum of a whole bunch of terms, and we'll talk more about that today, a little later today. Or if we don't get to it today, it'll be next time. A monomial is just a single term. Mono means one. So it could be a number, it could be a variable, or it could be a product of a number and a variable. Those are our options for a monomial. So examples would be things like, like 3 or x or negative 2x or pi x to the fifth. Those are all just examples of monomials. Or we could even have one, we could even have a more advanced one that's something like this. It could be like, how about 2x squared y z to the fourth. It could even have multiple variables in some cases. Okay, those would all be examples of monomials. Okay, so when we're simplifying monomial expressions, and this will apply to polynomials too when we start working with polynomials, we have to have a good, firm understanding of our exponent rules. And you guys all know this stuff. You're going to be able to tell me all the answers, but we're going to get a little practice before we jump into polynomial arithmetic, for example. So the product rule. Product rule just looks like this. Product rule says that if we have some base a to the m times a to the n, what's that equal to? What do I do if I multiply like bases? I add the exponents, right. And let's look at the anatomy of a power real quick. If I do something like, what if I have something like b times, I don't want to use b. What if I have something like, oops, 2x cubed. What are the parts of that? Well, the 2 is what we call the coefficient, right? Coefficient is any constant that's multiplied by a variable, okay? What about the x cubed? Well, the x cubed taken together is what we call a power. Boy, these pens, they did something over break, and nothing works anymore. Inside that power, there's two parts. We've got the base, right, which is what's being taken to an exponent, and then we've got the exponent. Okay, so there's the anatomy of a monomial, the parts, the various parts, okay? So the product rule says that if we're taking a product of powers with like bases, we simply add the exponents, and you guys knew that. I knew you would. So for example, x squared times x cubed is x to the what? To the fifth, okay? Okay, what about the power rule? Okay, so this is the one, and I don't care if you know the names of these. It doesn't matter. You just got to know what to do when you see this stuff. The power rule says, what if we take a power to a power? So if I have a to the m to the n, what do I do if I take a power to a power? Multiply the exponents. Good. So that's the same thing as a to the m times n. So my example would be if I take x squared cubed, I get x to the sixth then, right? Okay. Quotient rule. If I have a to the m divided by a to the n, so if I divide like bases, what do? You subtract, okay? So I get a to the m minus n, but I like to throw throw you a little curve on this one. It's also convenient for us to combine the quotient rule and the negative exponent rule into one form. And let's jump down to the negative exponent rule for a second. If I have a to the negative n, what is that equal to? It is. It is. So a negative exponent in the numerator always corresponds to a positive exponent in the denominator. So there's two parts to this. I want to write this two ways. And usually it's not written this way, but I think it's important to realize this. That's 1 over a to the n. The other possibility is 1 over a to the minus n. What does that equal? What do you think? 1 over a to the minus n, a to the n, exactly. Because that's like saying 1 over a to the n, right? And if I have a fraction in the bottom, don't I just multiply by the reciprocal? Okay, so there's a way to think about that then. You can simplify your thinking on this, and the way to think about it is a negative exponent in one part of a fraction. And when I say part, I mean numerator or denominator, right? Top or bottom. A negative exponent in one part of a fraction always corresponds to the positive equivalent positive equivalent exponent in the other part of the fraction. Negative on the bottom gets bumped to positive on the top and vice versa, okay? So if we combine that with our quotient rule thinking, look at these examples. If I had something like x to the fifth divided by x squared, well, the answer is just x cubed, right? X to the 5 minus 2. Okay, but what about this one? It's dumb pens. Why is it doing that? I don't know. What if I had something like x to the fourth divided by x to the seventh? Gosh, these things are just driving me nuts. You can't read that. X to the fourth divided by x to the seventh. What's that? Okay, good. So it'd be x to the negative third, which is the same as 1 over x to the third. Okay, is there a shortcut? Well, yeah, there is. If in the instance where the number on the exponent in the bottom is bigger than the exponent on the top, we might choose to do something like this. A to the m divided by a to the n equals 1 over a to the n minus n minus m, okay? So how do we think about that in the easiest way? Well, wherever the power is bigger, we could say that we're going to keep the variable where the power is bigger and subtract the other exponent. Okay, does that make sense? It's just a way for you to condense the steps when you're dealing with exponents. Okay, it's not anything profound, but it does make things a little simpler. Everybody see that? So here we would, instead of making this 2 steps, this second example we looked at, we'd say, okay, well, 7's bigger than 4, so we're keeping the x on the bottom and we're subtracting the 4 from the 7 on the bottom. Okay? All right, what about the 0 exponent rule? What is a to the 0 equal to? This is a weird one. It's equal to 1. Yeah. I don't have time to do this today, but I'd really like with you guys, I'd like to do a little proof of that for you. I'll try to work that in this week sometime, and then some dead time. It's kind of interesting how you can show that. So an example, a couple examples. If I have something like, if I had something like x to the 0, it's equal to 1. But more interestingly, I could have something like 3 x over 4x to the 5th z to the 7th plus 2/3 to the 0, doesn't matter. If it's to the 0, if I have some base, no matter how complicated, to the 0 power, it's 1. Everybody see that? Okay. Okay, power. So there's a couple additional ones I wanted to add that weren't included. The power of a product rule. Okay, so what about this? What if I've got something like a times b to the m? What's that equal to? How could I rewrite that? For example, what if I had 2xy cubed squared? What would that equal? Okay, yeah, you can think of it like distributing the exponent, exactly. So a times b to the m would be the same thing as saying a to the m times b to the m. So over here, we're going to have to take each of these factors that's being taken to a power. I've got to take each of those factors to that power. So 2 squared is 4, x squared is x squared, and y cubed squared is what? Y to the 6th. Okay? I'm sure you've seen that one before. Power of a quotient rule, same idea. If I have a divided by b to the m, do the same thing, right? I can write that as a to the m over b to the m. So an example would be something like, what if I've got 2x squared over 3y cubed cubed? Not only do I distribute horizontally, I also distribute vertically in this fraction, okay? So I'd end up with 2 cubed is 8, x squared cubed is x to the 6th, divided by 3 cubed is 27, y cubed cubed is y to the 9th. Okay, here's a counterexample. Here's the other thing I want to include that people oftentimes want to do. And this is a big no-no. A plus b to the n is not equal to a to the n plus b to the n. Okay? But you see why that is? What am I taking to the n? I'm taking the binomial a plus b to the n, right? And so what that really looks like is a plus b times a plus b times a plus b. And if I were to number these, this would be the first, that would be the second, that would be the nth product. So that's actually very complicated, right? A plus b to the n is a lot of work. It's a lot of work to figure out what that is because I've got to do a lot of multiplying. I would have to multiply a times b, get an answer, simplify it, then multiply times a, that whole thing times a plus b again, simplify, then multiply by it again and simplify. Or there's some shortcuts that I'll show you for that. But it's not so simple. It's not just equal to a to the n plus b to the n. Okay? All right. So let's just go through a couple quick examples. We'll skip down to some hard ones here. How about Let's look at, I'm going to make a couple up. I'm not satisfied that these are hard enough. Let's look at number 5. That's a good one. So number 5. And I'm going to cut and paste here. So this, we can make this a little bigger. How about? Okay, how do we think about this? Suggestions here. It looks a little bit awkward to have that 2/3 next to the r squared and the s to the 7th in that first term. Okay, different people approach this different ways, but when I look forward into what we do in calculus and beyond, it pays to write things as rational functions. So it pays to write things as one big denominator and one big numerator and work on it that way. So the very first thing I would do here is I would say, let's turn this guy into, make a fraction bar, and it's going to look like 2r squared s to the 7th over 3 quantity squared. Now, one thing that allows us to do is it allows us, we can't do anything in this case, but sometimes when we do that, we're able to do some simplification inside the parentheses. We're able to cancel some stuff vertically, for example, okay? Times, we'll do the same thing to this guy. So this is going to be on top, we're just going to get a 1 times r cubed times s divided by 6. Okay, makes sense? So we write those as with fraction bars as just big fractions. Now we'll apply, what comes next here then, by order of operations, if we want to simplify this? Can I multiply those two expressions yet? What do I have to do before I multiply with order of operations? Yeah, I've got to deal with the exponent, don't I, right? E comes before m in PEMDAS, right? So we got to deal with this guy. So I'm going to distribute that all the way through to all the factors. Now, nothing is being added or subtracted in here, so we're okay, right? This mask's killing me, sorry. So if we do that, what's that going to give us then? We're going to get from this first term, if I distribute the 2, I'm going to get a 2 squared is 4. R squared squared is, you guys just say it out loud. R to the 4th, good. S to the 7th squared is S, good. The 14 divided by what? 9? Times R cubed S divided by 6. Okay, now the advantage of this is, look, we've just got two big fractions. Now we get down to multiplying with the multiplication step for PEMDAS, right? Well, when you multiply fractions, how do you multiply fractions? Yeah, just straight across, right? Straight across. And we have the additional advantage of being able to even do some cross-canceling then if we're multiplying fractions, right? So we could, for example, cross-cancel here. We got this 4 and this 6. We could reduce that to a 2 and a 3. And why are we able to do that? I know that's a mechanical step for us, but the reason we're able to do that is we can effectively just extend that fraction bar. So we've got a string of products on the top and a string of products on the bottom, and multiplication is commutative and associative. So why not line up the 4 over the 6 together and reduce that fraction? See what I'm saying? We're not going to do all that. That's unnecessary. We could do it in our head, but that's what we're really doing when we cross cancel like that. We're taking advantage of the fact that these are all equal factors on the top and equal factors on the bottom, and we can reduce any pair of factors that we want to, okay? Then the other thing we end up doing here, so we're just going to multiply straight across. Now I've got a 2 on the top, and I can use my properties of exponents. So I'm going to commute these factors so that I'm going to multiply them in the order in my head. I'm not going to do this on paper, but in my head, I'm going to multiply 2 times r to the 4th times r cubed times s to the 14th times s to the 1, right? I'll multiply them in a convenient order. And then what am I able to do here if I multiply those like bases? What is that? R to the 7th. Okay, good. S to the 15th. I don't know if I'm going to be able to squeeze that in there. I don't think I can. Man, this is really frustrating. Divided by, on the bottom, I've just got 9 times 3 is 27, and we're done. Okay. All right. How about, I'm going to make up another one. So what about this? What if I've got okay, what about that? If I follow order of operations here, what do I do first? Okay, so exponent comes before division and multiplication, right? But before anything, we've got grouping symbols, right? And we've got this entire quantity that's being taken to the -2. So whatever's being taken to the power, that's internal to this power, right? That's grouped inside of the exponent. Everybody agree? So we should be able to simplify everything in there first, okay? That makes life a lot easier because look, there's a lot of stuff we can do there. The 12 over the 18 reduces to a 2/3. We get much smaller numbers to deal with when we're having to apply these powers, right? So the first thing is we could do something like this, right? We could make that a 2 and that a 3. Now look, we've got some quotients of like bases. We're dividing like bases there. Okay, so what are we going to get? We've got a 2 on the top and a 3 on the bottom. Where are the x's going to stay, top or bottom? Say it again. Top, good, because we have, it's going to be what power of x on the top? Yep, x cubed, right? 5's bigger than 2, so we keep the x's on top and subtract the bottom exponent from the top. We get 2x cubed. What about the y's? Bottom, get a y squared on the bottom. See how easy that is? Think about it that way. You skip those steps to the -2. Well, what about that negative? What's our negative exponent property do? What would, a couple quick examples here. What is x to the -2? Agreed? Okay, how about what is 1 over, actually, let's do it. I want to do this. Ooh, this will be, oh, this is tricky. I like this. Okay, hang on a second. I'm going to change that. What is x cubed to the -2? One over x to the 6th, isn't it? Good. It's x to the negative 6, which is 1 over x to the 6th. What's 1 over y squared to the negative 2? It'd be y to the 4th, wouldn't it? It's 1 over y to the negative 4th. So that's the same as y to the 4th. Okay, so now what if I combine those two ideas? And then I'll let you out of here. What if I have x cubed divided by y squared to the negative 2? Do you see that I'm flipping this whole thing, right? So the moral of the story is this is really cool. What you can do, if ever I have, oh darn it, if I ever have a fraction taken to a negative exponent, all I have to do is flip the fraction and make it to the positive. Everybody see that? That's really cool. So we get y squared over x cubed to the positive 2, which makes it simple. I better let you go. Okay. What's that? Oh, you have a copy too? Oh, yeah. I forgot to have you do that. Wipe them down real quick. I'm sorry. I got to let you guys out of here quicker. Say it again. Yeah, or if somebody, I'm going to make it somebody's job in here, somebody who's really organized, to remind me with like 5 minutes to go, so you guys can just do the wiping while I'm teaching still, and then we don't have to go through this exercise. I agree that if we all did it at the beginning, if everybody did, it would be better that way. Yeah, I'm going to suggest that. Yes, you do. Yeah. Okay, well, that's perfect then. We could do that. So let's see, for you, that'll be Wednesday's morning. So it'll be on Friday. The morning session is going to be the office hour session. So you can do it then. Okay. Perfect, yeah. Mm-hmm.